Hello there, and thank you for joining us today. I know you're joining us from all across the globe, so you're very welcome to this, the first in a new series of webinars from Impedans, where we will focus on plasma measurement and plasma diagnostics over the next few months. At Impedans, we specialize in high-resolution plasma diagnostic solutions, and in this webinar, we're going to focus on the Langmuir probe. But just to encourage everyone at this point, although your mics are silenced, we would really encourage you to participate by entering your questions into the chat box. If we don't get a chance today, we'll certainly follow up in the coming days, either in written form or we can schedule a meeting with you to answer your own specific questions. But please do treat it as, a question and answer session today. We'll have a half an hour once my colleague has finished presenting here, and we'd be delighted to have a chat with you. Just to introduce you to Tom. Tom is our Chief Product Officer here at Impedans, and he spent the last 15 years working in RF-driven plasmas. So together with the rest of the team, they'll be available to have a chat with you afterwards or in the coming days. So you're very welcome, and I'll pass you over now to Tom.
Thanks very much, Declan. We still have people joining in the room, but I'm going to share my screen and we'll get started on the presentation. I recognize a good number of names in the meeting room, so thanks to those who know me for coming along. I'll share my screen and present. Okay, and let me know when everybody, sorry, Declan, can you let me know if my screen is shared? Or let me try presenter mode again, sorry.
I can see the screen at the
moment. There we go.
Yeah.
That better?
Yeah, all good, we can see you. And the screen?
Perfect, and the presentation's full screen, yeah?
Yep.
Excellent, all right then. Right, so this, just so you know, this is being recorded, so afterwards we will we'll share the slides and we'll share the recorded version of the talk. So thanks for the introduction, but yeah, my name is Tom Gilmore. I'm the Chief Product Officer here at Impedans. And on the call, I also have a number of my colleagues from the Impedans support team. So they're a group of plasma physicists working as application engineers here, all of whom's job it is to help people understand these things, not just with our own sensors, but to have general physics conversations. The topic of today's webinar is on Langmuir probes. I want to focus on the basics of the Langmuir probes. I will be showing the mathematics on the screen, but if you wanted to build your own homemade probe, I'm going to show you how to do that. And I'm going to show you different, what's important to measure, what's important to take into account. And I also want to focus on practical applications in this talk. So let me go to the next slide. So in this webinar, we'll go through a few different sections. We'll do a very, very quick introduction to plasmas, which is where the Langmuir probes are used and why the Langmuir probe was invented. I'll speak about the Langmuir probe basics in terms of what is it, what's it meant to do, what can it measure, these sort of basic things. Then we'll go and touch on the design and construction of a Langmuir probe. So if you wanted to build one, how do you go about building it? What are the key things you need to take into account, and so on. Then we're going to go into the physics of the Langmuir probe. So we're going to talk about how to understand the data that it gives out. So it gives you an IV curve. What do the different sections of that mean? What information can you extract from the different sections? And in this portion, we'll show you the theory. Now, all the maths will be on the screen. I'm not going to talk through it fully, but you can refer to it later after the talk. And then the way we'll end the presentation is by going through practical applications where the Langmuir probe has helped people solve various problems or to develop their plasma source or to develop the process that they're working on. So a lot of practical real-life examples of where you'd use it over a broad range of different applications. So not just semiconductor, but we'll touch on thrusters and we'll touch on different source types. Okay, so let's get into it. Let's do the very brief introduction to plasmas. So I think most of you on this call already know what a plasma is. So this is more for those students who are new to this. If you want to think of a plasma, it is essentially a collection of positively and negatively charged particles. It's an ionized gas. By ionized, it has specific properties that make it be defined as a plasma. But as a general rule, it exhibits a collective behavior, and it has it's overall an electrically neutral system. And there are many, many, many types of plasmas. So I list some of them here. But in essence, you have dense plasmas and weakly ionized plasmas. So a dense plasma, for example, would be like what you'd see in a tokamak, or the sun would be a very dense plasma. And then you have, the weakly ionized plasmas, which is maybe what you'd see with the solar wind or something like that. You have low temperature plasma, and you also have thermonuclear level plasmas. We also classify them as collisional and non-collisional when we're dealing with different pressure ranges. They can be magnetized and unmagnetized, and so on. But in this talk, the key plasmas that we're going to be talking about are what you'd call low temperature, low pressure plasmas. And they're the ones that are used day to day in the industry to do plasma processing. So by low temperature, I mean they're on the order of, basically room temperature and a little bit above room temperature. So 300 to 600 Kelvin. They're relatively low density plasmas with pressures on the order of, 0.1 Pascal to about 1,000 Pascal. So in other words, below 1 torr pressure or sort of below 1 millibar pressure. They'll be the most commonly used plasmas and where Langmuir probes are most often used. And we'll also, the plasmas that we're talking about today, or where Langmuir probes are applicable, it can be collisional or non-collisional. It doesn't really matter. The theory takes into account what we're looking at. In the three images here, the one here on the left is a very typical, basic CCP plasma that you'd see in many research labs. Whereas the one on the right is the internals of a tokamak, which would be an intense plasma that's designed to be an energy source. There are also atmospheric plasmas like plasma welders or plasma jets, which are commonly used to like treat surfaces and treat materials and so on. And you can use Langmuir probes for some of those, but anyway, let's continue. So, what are the applications of plasmas? I mean, the very first application of plasma really was light bulbs. The Langmuir probe was invented to sort of improve the lifetime of light bulbs and understand what goes on inside them. But in general, plasma are used in a lot of different industries. Probably most famously is the semiconductor industry, where they're used to etch materials and to deposit materials to sort of slowly build up the transistors or whatever other semiconductor components are being built on the chip, or other semiconductor components. And there are challenges in these industries. Main challenge is to follow Moore's law, but what we want to do is, what the industry want to do is to be able to measure these plasmas, to be able to, to measure something about it so that you can, design your process, make predictions on how it's going to behave, and so on, and to tailor your plasma to get the results that you want. And there are many ways of achieving that. So if you see here, this is a graph which is showing a lot of different types of plasma diagnostics. So there's magnetic probes, there's light-based things like interferometry. You can use sort of in situ probes and all sorts of different things. But the focus of today's talk are what are called electrostatic probes. So these are probes that are measuring voltages and current and so on. And in particular, we're going to focus on the Langmuir single and double probes. Okay. So let's get into it. Oh, first typo that we see. We might see a few more. Langmuir probe basics. So what is a Langmuir probe? So a Langmuir probe, in a sentence, is an electric probe or an electrostatic probe, which is used to measure the local plasma parameters. So the idea is, it is simply a piece of metal which is situated somewhere in the plasma, where you apply different voltages with respect to the chamber ground, and you measure the current that results from changing these voltages. And that gives you a lot of information about the plasma. So if we look here on the left side, you can see a zoom in of what the plasma measurement tip typically looks like. So you simply have a piece of wire, typically tungsten or something that can survive high temperatures. That's surrounded by some sort of insulating material. And then there's some other material which helps, protect the probe from the plasma. And then these are all usually connected to a shaft, and that shaft will go out to some sort of vacuum port. In a few more slides, we'll actually show you a more detailed view of how you construct a probe. But in essence, it's a controlled measurement tip that sticks somewhere in the plasma, and you take the measurement at that point. And what does this measure? So this measures plasma density. By plasma density, we mean the ion density, so how many ions per unit volume, how many electrons per unit volume, and so on. The electron temperature, which is a very important number for working out what kind of chemistry goes on inside the plasma. In reality, the electrons have a distribution of energies, but we usually boil that down to one number, which is electron. It also measures the floating potential, which is important if you have a substrate inside the system, which is floating. It gives you then, you can use that to work out, how high in energy these ions or whatever will bombard that surface. Also, you can measure what's called the plasma potential, which is the basically what voltage the plasma is at with respect to the chamber ground. Also good for giving information about ion impacts, and so on. The sort of plasmas that you can use Langmuir probes in are the most common available. So like semiconductor plasmas, which would be CCPs and ICPs, various sputtering systems, etching systems, IPIMs, PCVD, and so on. So if you look at the image on the right, you can see kind of a typical installation. So this is just a photo from the Impedans lab, where a Langmuir probe is inserted in a capacitively coupled plasma. So it's two plates separated by some distance. The plasma is struck in between there. This is a radio frequency driven one. This is the probe shaft, and at the very end is the little probe tip. And we're taking a measurement at that point of all these parameters. If we go into a little bit more depth, there are many different types of probe that you can make. Now, most of this talk, we're going to be speaking about what's called the cylindrical probe, where you have a long, thin tip, which is taking the measurements. But there's also what are called planar probes, which are just sort of a flat surface that take measurements. And there's spherical probes. So just imagine a big sphere at the end of the probe. And I'll talk later about why you'd use the different types in different situations. But in general, the cylindrical one is the most used and the most easiest to build as well. When you're taking data with Langmuir probes, what you get is this. So I'll talk you through this diagram, and we're going to focus in on this diagram in the theory section. But essentially, on the x-axis, you're sweeping a voltage. So you're applying a voltage to that measurement tip with respect to the chamber ground, from a negative potential to a positive potential, typically on the order of minus 50 to plus 50 volts. In this example, it's minus 20 to plus 20. And the idea is that as you sweep that voltage, you measure the current that results. When the current is sufficiently negative, when the voltage is sufficiently negative, you're only collecting ions. So that's giving you information about the ion density. When it's sufficiently positive, you're collecting electrons and repelling ions. So that's giving you information about the ion density, the electron density, sorry. And then there's a sort of region in between, and that gives you information about the electrons, the electron energy distribution function. So how many, what the energy profile are of the electrons in the chamber. So we'll go into this in a lot more depth in a couple of slides. Now this is just an example piece of data. This is also to show that the different probe types actually behave differently after a certain point, which is essentially to do with how the probe interacts with the plasma. The different shapes expand the sheath. But we'll get into that. Here's a screenshot from our commercial Langmuir probe. But this is to show you an example of real data. So you can see there's the ion current saturation region. There's this sort of transition region, and then you get into the electron saturation region. And because this is a cylindrical probe, then at that point you get this sort of curve upwards as you apply higher and higher voltages. You can also see in this diagram that you can't really see it in the slide, I think, but down here, this is the zero current measurement. So the ion saturation current is very, very low compared to the electron saturation current. We'll explain why a little later. But from this curve, you can pull out information such as the ion density, the electron density, the floating potential, the plasma potential, and also about the electron distribution. So this is like a big list of everything that you can measure. And each of these plug into either plasma models or into models on how the ions are going to interact with substrates that are placed inside the chamber and so on. Yeah, so let's first show you how do you build a Langmuir probe. So if you want to go build one, what do you need? So you must consider a few things. So Langmuir is going into a harsh environment. So it's typically going to be, some high vacuum level. You're going to be using possibly exotic chemistry. You're going to have all these charged particles moving around and so on. So you have to build a probe to withstand this harsh environment, to keep the vacuum level. And also, you have to consider a few things to make sure that the data you get is correct. So what kind of things do you need for a probe? So this is kind of a cross section of a kind of very typical Langmuir probe build. Like if you want to build one in a lab, typically you use some sort of BNC connector where the central pin is the measurement and the outer is the ground reference. The outer shield is the ground reference. Then you'd have some sort of thin, rigid or semi-rigid coaxial cable going down the ceramic tube. So the point of the ceramic tube is that you go all the way down to where you want to actually take the measurement. The stainless steel on the outside is not necessary. Like you can just build it with a ceramic tube. And then at the end of the probe, so where you have the center core of the coaxial cable, you essentially want to have a needle-thin piece of metal that comes out through the structure that I mentioned earlier, where you have a ceramic piece that insulates the metal. So what kind of, I can explain why you do all this. So you want to make it so that the measurement tip, you only want to measure at that point or over that region. So that's why you have that's one reason why you have the insulating material. So you can have the tip sticking out, but you have it only where you want to. In addition to that, the metal tip has to be very thin to use the theories that we're going to describe later on. So you want to make it so that the tip is maybe a few millimeters long, maybe it's on the other 10 millimeters. But you want to make it that the thickness of the probe for the theory to work best is like a fraction of a millimeter. So maybe a third of a millimeter or something like that. So you need some support structure to hold that in place. Also, in general, you want to taper down from where you have the probe to so from where you go from the shaft to where you have the probe, because this shaft can perturb the plasma. Okay, but the plasmas have a property that they're kind of self-shielding over a distance of several Debye lengths, which is something this measures. So the idea is that you want to start off with your, you have your thick shaft length, but you want to taper down and taper down and taper down, so that by the time you get to the tip, there's a minimal perturbation in the area where the tip is actually stiff. Okay? There are some other considerations. So, for example, when you're doing this IV sweep, I mentioned earlier that the electron saturation region, you draw a lot of current, so it could be on the order of many milliamps or even an amp of current. So that means that this material can get quite hot. It's a very, very thin piece of metal. It's going to have a bit of resistance. So you want to choose a metal which is suitable for high temperatures. So very typically, like tungsten is the most common that you use. Now you also have to consider the chemistry that's happening inside the plasma. So maybe platinum or tantalum, if you're using oxygen plasmas or some sort of oxidizing material, because otherwise tungsten will oxidize quickly. I mentioned the coaxial cable, and I mentioned the needle and the ceramic. The only other thing you need to take into account is the vacuum seal. So you want to use a typical flange or a rubber O-ring and so on. In terms of vacuum seal epoxy, you want to use something like Tor Seal in order to make sure that you hold vacuum. So in general, the requirements are you want to sustain the high heat loads from the plasma. You don't want to be eroding everything by sputtering, so use a ceramic material or use a stainless steel material. You taper down so that you don't perturb the plasma overall. And you want to make sure that the probe is not reflecting particles at the tip or anything like that. Tapering is quite important. In terms of the circuitry, it's quite simple. You need to provide a change your bias voltage with respect to ground, and you want to measure the current that comes back. So some variable voltage supply, and some sort of ammeter. That's it. And the installation is fairly typical. Like you have it's very simple. You just have some sort of port. You have your vacuum seal. You have the ceramic shaft, and you make sure the tip is where you want it. There are a couple of considerations here. Like you want to make sure that the Langmuir is actually inside a plasma. If it's too close to an electrode, you could be inside a sheath between the electrode and the plasma, so you don't measure anything. You want to be actually in plasma. Okay. One last consideration. Everything I mentioned so far is applicable to microwave plasmas, DC plasmas, and so on. There's one extra consideration when you have a radio frequency driven plasma. Essentially, because of the radio frequency, with this varying voltage versus time, we have to contend with that sort of voltage change happening over time. So the way that you make sure that your data is good is that you introduce inductors. So you introduce inductors which have a resonant frequency around the driving frequency of the plasma. Or in other words, you want to make it so that if you're driving a plasma of 13.56 megahertz, you have an inductor in line with that measurement, the central pin where you're doing the measurement, which has a very high impedance to ground. So by high impedance, I mean, on the order of at least 100 kilo ohms up to a mega ohm is a good sort of range. So what this is saying down here is that basically the probe impedance must be, much greater than the plasma impedance. But as a general rule, you want it to be on the order of 100 kilo ohms or more. So this allows the tips to sort of float with the RF and make sure you get a good measurement of the plasmas over time. You also need to make sure that the filters are placed as close as possible to the tips for the tips to float. The further away they are, the less effective they are at doing that job. If you don't put in these inductors, what happens is essentially your probe is kind of measuring IV curves when the plasma is in one state and another state as it's oscillating with the RF. So you get an average of those IV curves, and the data analysis doesn't make sense. When you have the filters in place, you should get the beautiful IV curve that I showed earlier. If you have filters in place but they're ineffective, the result is that your electron temperature reading will be too high. So your electron temperature of a plasma is typically like 2 to 7 eV, but very often it's on the low end, like sort of 2, 3. So if you're measuring 8 eV in a standard CCP system, it means that you have the wrong inductors in it or too far away from the tip. So high electron temperature is sort of a giveaway that you're doing it wrong. This diagram here is just to show, like, if you do a frequency sweep of one of these inductors, this is a log scale, maybe a bit hard to read, but this is the 100 kilo ohms line. You want to make sure that you have a very high impedance at that filter point. So in 10 minutes left, maybe we'll overrun a little bit. We need to go through the IV characteristics. So these slides that are coming up, they're going to have all the mathematics on it. I'm not going to go through the maths and the details, but I'm just going to give you an idea of what each region of the IV curve means and what you can get from it. So with an ideal voltage current characteristic, so again, you're sweeping a voltage, you're measuring a current. You have these different regions that appear. And as mentioned earlier, you have an ion region, you have an electron region, and you have a region in between that gives you different pieces of information. The theory which is used to analyze these curves, firstly, there are different theories available, but there's a few assumptions that you should be aware of. So you can't just assume if I stick a Langmuir probe in this plasma and I apply the formulas to my data, I get the right answer. No, you have to consider a couple of things. Here's a list of the typical assumptions that are made. So usually we're assuming a non-equilibrium. So that means that the ions are kind of room temperature, but the electrons are, tens of thousands of degrees Celsius, which is, on the order of 1, 2 eV. So we're assuming that we're in a bulk plasma that is homogeneous and it's, quasi-neutral. So that means that although it's a charged plasma, in general, the ion density and electron density is the same. So this means, if you're measuring in an ion beam with no electrons, then you're not going to get the IV curve you expect. we want to make sure that the mean free path of all particles are greater than certain characteristic lengths. Again, don't worry about this too much. We'll show you the maths later on. We're assuming that electrons and ions have Maxwellian distributions. So you can have plasmas with multiple temperatures for various reasons. But most of the theory we're going to show you assumes a Maxwellian distribution. But with the Langmuir probe, you can actually check if it's Maxwellian or not, and you can measure parameters in a different way. Yeah, so we also want to make sure that any perturbations to the plasma are confined basically to just the sheath around the measurement tip, and then we can take into account what impact that sheath that forms around the measurement tip has. So we're kind of assuming that the probe is not having a big impact, or there's no other major perturbation. That the only ones are just from that tip only. Okay. And we're also maybe, this is an assumption you don't necessarily have to use, but that all charged particles reach the surface of the probe are collected. So we're assuming that the probe is ideal. But there are various theories that can take into account things that make this not true. For example, orbital motion theory. So let's dive in a little bit. The first region of the IV characteristic is what we call the ion saturation region. So you may have heard of ion saturation measurement. The idea is that this is letter A in this probe, in this IV curve diagram. The idea is that's when a large negative bias is applied, and that negative bias repels electrons and attracts in ions. So you can make a safe assumption that you're only collecting ions in that region. Now, when we say like very negative voltages, the typical voltages you use are in the order of 60 to 80, minus 60 to minus 80 volts with respect to ground, will usually get you a good result. I mentioned all the maths, so I have a bunch of maths here. I won't necessarily talk through it. But the key thing is from this that, the ion current actually depends on the electron temperature. So this thing which is driving the chemistry in the plasma, electron temperature, is also driving the ion density. But from this, from this region, you can get information on the ion density. You can see here some of the input parameters. So, for example, the area of the probe, the surface area of the probe matters. So usually, when you use a long, thin tip, you can pretty much assume that it's a long cylinder, and then there'd be like kind of a hemispherical end. You want to make it so that the hemispherical is negligible, and this is like long and thin enough that you can just use the sort of area of this surface here as your collection area. This diagram here shows kind of what's going on the small scale. You have ions coming in from the plasma. The plasma is at a certain potential. The metallic surface is at some negative potential, and so ions are attracted in and electrons are repelled out. And like I said earlier, we're generally assuming that all the ions that collide with the surface are collected. Let's go on to the next. Afterwards in the Q&A, you can ask more questions about this, and we can go into much more detail. But I want to go through the different regions at this point. So the region on the right side of the IV curve is called the electron saturation region. And this is where you provide a sufficient positive bias that all the ions are being repelled and the electrons are being collected. So here's the same diagram again, where everything initially is at the plasma potential in the bulk plasma, and then we apply a large positive voltage. The electrons are attracted and ions are repelled. And from this region, you get information on the electron density. One thing to note in these diagrams, and this is not quite to scale, is that in the electron saturation region, you collect a lot more current than in the ion saturation region. So there's a little calculation here of, in an ideal situation that, the electron current is on the order of nearly 200 times what the ion current is. And it's to do with the relationship between, electrons having a very, very small mass and ions having a very large mass. Like just to show you the example from earlier on, the ion saturation current was, very nearly zero, whereas the electron current was on the order of milliamps. Like this is on the order of 30, 40 milliamps here. So you have to take that into account when you're designing your current measurement circuit, that you have the appropriate sensitivity to get good data with good signal to noise in the ion saturation region. But also you need to consider that you don't saturate your electronics by drawing way too much current in the electron region. So that's why also it's very good to have a very small surface area for the probe collection, so that when you're drawing electrons, you're not drawing way too much. Conscious of the time, so let's go quickly. This middle region here is called the electron retardation. So in this region, you get to the point where electrons start contributing more and more and more to the current. At some point, when they're equal, this is called the floating potential of the plasma. So what this means is if you put a substrate somewhere in the plasma, sitting on a surface which is not grounded or anything, it will float to that potential. It will become that voltage at respect to ground. So it's all to do with the balance between ion flux and electron flux. But basically, in this region, as you go from no electrons contributing to a few to no ions contributing, this is giving you information about the electron energy distribution. Okay, so we call this the electron energy distribution function. So in this diagram, basically, as we're approaching what's called the plasma potential, we start to collect more and more and more of the electrons. So we start to build up this profile. So initially, only the high energy electrons can make it past the potential that we're applying, and then you get lower and lower and lower ones. And then it's a plasma potential at this point, get back to zero. Let me show you some sort of real data. So this is an electron, well, this is called EEPF, but it's essentially an electron energy distribution function. And note that the y-axis here is on a log scale. So really, most of your electrons are on the order of 2, 3, 4 eV. Then you have a tail of much, higher energy electrons, but considerably less. The reason why you want to measure this is that this information here is what you plug into chemistry models of a plasma. So it's the electrons that drive the chemistry that's going, the electrons and the gas temperature. And even the ionization that's happening inside the plasma. So if you remember, ionization typically is like more than 10 eV. So in reality, a lot of what's going on inside the plasma, like the ionization of the neutrals that are present, is mostly driven by this tail end of electrons, which is a very low amount compared to what you have at the low energies. Now, the low energy ones do contribute. So for example, certain many particles have what's called a metastable state. So you can have you can take an electron from the ground state to some high level but stable state, and then another electron can kick that out so the particle is ionized. So you have this multi-stage ionization process. So if you've ever, added a bit of argon to your plasma to help it strike, because otherwise, like say it's hydrogen is not striking, and you add a little bit of argon and then it strikes. It's basically because you're playing with this electron energy distribution function, and you're playing with, getting the right amount of electrons at the right energies to get the plasma flow. So I've gone through the theory section quite quickly, but we'll share this afterwards, and we can go into much more detail separately in different conversations. So what I want to get into here is like the applications of these Langmuir probe measurements and their industrial applications, and I want to give as many real examples as possible. So to start, I want to identify like where can you use Langmuir probe, because you cannot use them everywhere. You cannot use them in every plasma. So where is it applicable? Well, the majority used in industry. So these low temperature plasmas, which are the room temperature and slightly above plasmas. So these are very typical CCP and ICP plasmas that you have in the industry. You can use them in deposition plasmas, so magnetron sputtering, high PIMs, PCVD, provided that you clean the tips regularly. And cleaning the tips, because the idea is that it's a conducting surface. So if that's coated with an insulating material, you can no longer draw current when you apply voltage. So the way that you keep the tips clean is when the plasma is running, you regularly apply a large positive voltage, like under 50 volts or something. So you draw a huge electron current to the point where that tip glows red hot or white hot. And by choosing material like tungsten, you can safely do that without damaging the tip. And that will boil off all the materials that are deposited on the tip. So yeah, you can clean a Langmuir probe in situ. But you have to do it very quickly, because if you're too slow at cleaning it, then the tip is coated and you'll have to take it out and manually scrub. It can be used in etching tools and reactive ion etchers. It can be used to characterize thrusters, and also things like pulsed plasmas. And you can use Langmuir probes in high pressure plasmas, but there's a caveat which I'll explain later. Where are they not applicable? So generally, they're not applicable in hot plasmas, like fusion plasmas. It's not impossible to take measurements in plasmas that are very hot. So let's say you're monitoring combustion, and the local temperatures are like 3,000 Celsius or something. The way that you do that is you have to, put the Langmuir probe on an actuator and sort of make the probe go in, take a measurement, and pull it out in a fraction of a second, which is done, to get measurements in these situations. But generally speaking, it's hard to do. You have to be able to trigger measurements and take them very quickly. It's a bad idea to use them in highly reactive plasmas. So you have to choose the materials you make the probe with to be used for different chemistries. So like I said, platinum or tantalum is much better for oxygen plasmas than tungsten. Tungsten is pretty robust, but in general, consult with a chemist or have a look online at reactivity tables to judge where you can use it. So high temperature CVD is normally where Langmuir probes are hard to use. So very high temperatures, high deposition rates, very tricky. And also where very high voltages are present. As I mentioned, the most common type of probe is the thin metallic tip like a needle. So if you use a plasma like a dielectric barrier discharge, where the plasma is very local to a surface which has tens of thousands of volts, placing that metal tip very close, you're just going to arc to the tip and destroy the probe. So there are some limitations. In terms of capabilities, what do you use it for day to day in the field, right? So obviously for research and development. In the semiconductor industry, one of the key things are uniformity. You want to make sure that the plasma at the center of your tool is the same as at the edge. And uniformity measurements are key. And normally you do that with a waveform. But a much easier way of doing it is with a Langmuir probe with a linear drive that sweeps the probe across the surface, and from that you can measure uniformity very well and quite quickly. I'll show you some example data of that. You can use it to characterize thrusters, so you can have a look at, the ions that are emitted and some electrons. You can have a look at, are they all forming a nice narrow beam like you want in a thruster, or is there much waste, or that sort of thing. So you can use it for angular measurements. Also in ion beam tools, you can use it to kind of get an idea of beam divergence. And I'll show examples of that. They can also be used to look at the ignition of a plasma, or looking at pulsed plasmas and how they evolve as the plasma turns on and off quickly. And this is quite critical for designing like what chemistry results from pulsed plasmas. Because molecular plasmas, when you strike a plasma, evolve in a very complicated way as different energy absorption modes take effect, or as certain species are formed, they then become the dominant way that energy is being taken up. So you can even see sometimes when striking a plasma, a color change, like red to blue or something striking. So you can use Langmuir to study that. And also for optimization, like maybe you need to have a certain electron temperature to make the chemistry you want to sterilize something, or you need to have the right density to run your etch process sufficiently fast, and so on. So you can use these to judge that. So let me show you some real examples. So here's an example of uniformity measurements. And all the data I'm showing here is published data. It's all publicly available. So this is data published by Cyram, who are a manufacturer of microwave sources. And they've developed sources where they can actually they can play with many different sources to make it so the plasma is uniform. So this is using a Langmuir probe to rapidly develop this system and compare with simulations to get the 2% uniformity that they were aiming for. Like a Langmuir sweep can be gotten in milliseconds, so you can quite quickly scan across, get your plasma density data or electron temperature data across the way, and the density of the plasma across the way is going to be directly related to the uniformity you get across the substrate, obviously. So the next one. So this is an example of thruster divergence, where a Langmuir probe was sort of moved in line and out of line with a thruster to have a look at, where are all the ions present? Because obviously, depending on that divergence, you get more efficient or less efficient in terms of getting thrust per power. So these are some maps generated by the Langmuir probe, where you can clearly see where all the ions of the thruster are present. So this is a xenon thruster. And you can see sort of the evolution of the plume. And there are also maps of electron temperatures and so on here as well. Go to another example. So they can also be used to study, things like high PIMs, where plasma is only on for a very, very short amount of time, like 30 microseconds, 50 microseconds, and then off for a more substantial amount of time, in order to produce very high density ions, very high density plasmas to get, a high enough level of ionization to produce certain materials at the other end. So you can see here, for example, this is a graph of the pulse that's applied, and this is the evolution of electron density versus time. So obviously it peaks somewhere, towards the end of when the pulse is applied. So that's when all the energy is deposited. And then there's quite a long afterglow region where there's still, the plasma present, but it's slowly dying off over time, over the full cycle time. To give you more an example in another field, if we're looking at pulsed RF plasmas, which are becoming particularly important as a way of controlling ion energies in the semiconductor industry and controlling chemistries, is looking at the evolution of a plasma when you pulse it on and pulse it off. So here, for example, you can see this is a 1 kilohertz with a 50% duty cycle. So the power is turned on, left on at a constant level, and then turned off. But in reality, how the plasma reacts versus time. So these are when you take Langmuir probe measurements where you sync up the probe measurements with a delay. So you have a delay signal, and you're saying, okay, this measurement is actually happening to 10 microseconds from delay, 20 microseconds from delay, and so on, to build up these profiles. And you can see how the plasma takes time to strike, then it settles for a certain amount of time, and then there's a decay period. And sometimes in these strike periods or in these decay periods, you can get chemistries or voltages or other things that are not helpful for your process. And I think this was for a simple argon plasma, but this is for an argon-oxygen mix. But let's say if you had an oxygen-nitrogen mix, this evolution of the plasma gets quite complicated. You have multiple different slopes in the ignition period as different energy absorption mechanisms become dominant, and as new species are formed, and they become the dominant ion, and so on. So this gives you a good window into what's actually happening inside the plasma on a small scale. These are some other sort of similar idea time-resolved pulse measurements, where you see these sort of afterglow regions, and you can see the behavior changes versus pressure. And it's not linear. It's usually like how it behaves at low pressure, medium pressure, and high pressure can be very, very different depending on the collisionality of the plasma. So instead of relying on models or to benchmark models, you use these probes to get that sort of insight. Maybe because we're low on time, I'll skip by this. The last thing I want to cover is we mentioned today what's called a single probe. Okay, but single probes, I kept saying that the measurement potential is with respect to ground. Okay, so when you apply a voltage, it has to be with respect to something, with respect to a local ground. But not all chambers actually have a ground that's visible to the plasma. So you may be using a glass cylinder, or you may be using like a ceramic dome, or you may be using a chamber which has anodized surfaces on the inside. And in those cases, a single probe would not work because there's no ground reference. So when you're applying these potentials, you actually really badly disturb the plasma or even collapse the plasma. Like think of it as you're completing a circuit where the plasma is a conductor. If it's a completely open circuit, you can't draw current, or when you draw current, you're extinguishing the plasma. So there is what's called a double Langmuir probe, which is where you simply have two tips beside each other. So instead of the reference being the chamber ground, the reference is the other tip. You get a different IV curve. You get kind of an S shape, but this is a way that you can measure in these unusual plasmas. So high pressure plasmas where there's poor connectivity to ground, where there's no ground available at all. In these systems, you have to use what's called a double probe. And then you can get the ion density and the electron temperature again. So if you have a system that looks like this is an ITP system with a glass tube, although more often it's ceramic quartz, something like that, you need to use a double probe or the data won't make sense. So went a bit quick through the theory and ran a bit over time. but I'd like to just mention the literature we used. So we used Chen's Introduction to Plasma, Hutchinson's Plasma Diagnostics, also the Impedans Langmuir probe user guide has a huge amount of detail on the theory. And I'd like to give credit to the Impedance support team for helping write this talk. So these are all PhDs and using Langmuir probes for studying these sort of plasmas. So Andrew Verma, Artie Rowett, and Sean Knott. And also, some of the slides today were inspired by a talk given by Caroline Hain from Birmingham University of Applied Sciences. So just want to say thanks to Caroline for inspiring some of the sections of this talk. So thank you. I'll open it up to questions.
Yeah, thanks, Tom. Look, that's been a deep dive in a short space of time, so thanks a lot for that. Again, I'd just like to emphasize, if you have some questions, do pop them into chat. And if we don't get a chance today, we'll certainly come back to you in the next couple of days. Or indeed, if you'd like to discuss, a specific project, feel free to reach out and we'll set up a one-on-one meeting with you. So, Tom, just to take the first question here, why is it that an electron saturation current for cylindrical Langmuir probes is less than the spherical Langmuir probe?
Yep. So I may actually ask Sean or Artie to comment better on that. Let me go back to the slide. Oh, I have a lot of slides. I have to go way back. So go ahead. I hear someone's unmuted.
So the reason for that would be related to the growth of the sheath. In the case of a cylindrical Langmuir probe, it will grow basically as an R-squared effect. So as the sheath gets wider, it will basically grow the same way a circle would essentially grow. So the volume you're going to grow from will grow as R-squared. In the case of the spherical tip, it will grow with the volume of that, which is obviously an R-cubed effect. So it will grow a lot quicker as you increase the voltage.
Yep.
Okay, excellent. The next question, how do you identify if two different electron temperatures species are present in a plasma from IV curves, typically seen in filament-based plasmas?
Yep. So let me go down to... so actually, Sean again might be the best one to comment on this, but if we go to the electron energy distribution function, where is this? Yeah, this region here. So you'd actually see that clearly in the electron energy distribution function as two different slopes when you measure it. Yeah, and there's a different way of handling that in the theory. So again, actually, Sean's thesis was on this topic in particular, if you want to comment.
Yeah, so when you do the standard analysis, in the case of a bi-Maxwellian or just a dual temperature system, you'll essentially be calculating what is the screening temperature, which is the weighted average of the two based on the densities of the two processes. So the standard kind of EEPF won't calculate the two individual temperatures, but there are obviously other analysis that you can do to get the two individual temperatures, which is what my own work was on previously.
Yeah, basically you would see it in this. You'd see it in the EEDF. There's two different slopes when you have a dual temperature system. Am I correct in saying that, Sean? Would that always be the case, actually?
Yeah. Well, depending on obviously how separated the two temperatures are, the relative densities of them, and so on. If the density of one of them is, sub 1%, it's going to have a negligible impact, and so on. So you would need comparable enough densities, maybe even even 10 to 1 would probably be okay. But you would need it for the hot electrons, which are typically the lower density. You would still need them to be dense enough to actually register to have a significant impact on the EEPF. And my own research was actually in a filament-based plasma. So
one other comment here, and maybe Sean will add, is basically when you're to get the EEPF from this region, the easiest way is actually by looking at the second derivative of this curve. So again, Sean might be the best to comment here on the finer details.
Yeah, that would be it. You just look at the EEPF and determine kind of, are you seeing two you can then obviously just use the temperature that the theory is currently giving out, but you'd have to keep in mind it is the screening temperature, or basically which is just the weighted average. But otherwise, you have to apply a kind of a more or a different basically theory to actually determine them individually, which would be going back to the actual OML theory to deal with the two probabilities.
If whoever asked wants to have a more detailed conversation with us, or we can actually send you maths and send you examples and so on, send us an email. So like the main, I didn't mention in the talk, but if you email support@impedans.com, that actually gives you access to the whole team of support and application engineers and scientists. And we're pretty responsive, so we'll do our best to answer your questions.
Okay, another question here. Does the secondary electron emission from probe tip have any effect on the current measurement in thruster plume? Typically, thruster plumes have an ion energy ranging from 1 to 2 keV.
Yeah, so actually when customers ask us about measurements in thrusters, we actually typically recommend you don't use a Langmuir probe, but you use what's called a retarding field energy analyzer. So that measures the ion energy distribution function, or you can reverse the polarity and measure the electron energy distribution function. But that has a number of grids in it, and one of the grids is for suppressing secondary electron emission from the impact of the high energy ion to get the correct current measurements. So in most of the thruster characterization processes that our team have been involved in, they've used the retarding field energy analyzer, including one that recently got tested in orbit, which we're quite proud of. But anyway, but to answer that question, I don't know if Artie or Anshu or Sean, who've worked on these thruster applications before, if there's a comment on that. I think that's a true statement that it does have an impact, and it'd be hard to take into account.
Yeah, I would like to add here that if the ions are impacting on the probe with very high energies, like he said 1 to 2 electron volt, then there will not we have this ion saturation increasing at a much faster rate. We have.
Can you repeat the last sentence, Anshu? Sorry, you broke up for a moment there.
Yeah. So when there are highly energetic ions reaching the probe, we will not achieve this ion saturation region. This ion saturation region, in general, we have a flat line, but this will not be a flat one. This will be increasing when we are moving in higher negative voltages. It will be increasing at a much higher rate. So you will not observe ion saturation region.
Yeah, makes sense. So yeah, so basically this A section of the curve, like normally this is pretty much a flat line all the way, but you would see it as a slope. Okay, makes sense. Yeah. So in general, yeah, for thruster characterization, we usually recommend retarding field energy analyzer because it takes all that into account and suppresses that.
Okay, so how do you know if the Langmuir probe is being impacted by the RF-driven plasmas?
Yes, so I mentioned this earlier on, but basically the telltale sign is that your electron temperature is unphysical. So, you know, in a CCP system, very often 2 to 3 eV. If you're seeing a measurement like 8 eV or something like that, it's too high. So it's kind of hard to show. I don't have a diagram of it, but if you imagine that you have this IV curve here, so that's an IV curve for a plasma when the voltage being from the RF cycle is, say, high, and then when it's low, the whole thing is shifted to the side. So what you end up with is an IV curve that's kind of like an average between two different IV curves at different potentials. So you end up with this sort of weird kind of elongated S shape, like so basically the whole electron energy distribution region becomes quite noisy and distorted. Yeah, so when you do the analysis, if you're getting like 8 eV or 10 eV or 12 eV electron temperature, that's really a telltale sign that your filters are not appropriate or too far away. Yeah, so like when we build probes for our customers, we always recommend that like we put the inductors right up at the tips, but but for various reasons, sometimes customers, like say you can get higher temperature probe if you put the tips further back towards the wall of the chamber, because you have lower temperature variation there. But the result is that electron temperature goes out of whack.
Okay, I know we're coming up on 5 minutes here, but which is the best to use for a model with a high energy tail?
I'm not quite sure I get the question. It could mean a few things.
Which is the best to use for a model the high energy tail, or to model high energy tail, is it?
Okay, is that in terms of getting the data out? I don't know if Sean, that would make more sense. Do you have a comment?
In relation to two temperature plasma.
Oh, okay. This is definitely Sean's question.
Sean there?
Might be muted.
I think Sean popped out and came back. I think you might just move on. I think you might have covered this at the start. Are there any situations where you need to use the other measurement tips instead of the single probe?
Yeah. So actually, I never really covered. Sorry, was Sean back there?
No, I don't think we have Sean. Yeah.
Okay, no problem. Yeah, so I never actually went into detail of why you'd use the different probe tips. Let me go back to the image of the three of them. Goodness, there we go. So where would you use the different probe tips? Generally, the vast majority of the time, you use this thin, narrow tip to take the measurements, and that's sufficient. The place where you use the spherical probe is typically when you have a very, very low density plasma. So the idea is that with the spherical probe, you have much larger surface area to be collecting ions. So for example, if you were doing measurements in space for the solar wind or in the ionosphere or in the moon or something like that, you'd actually want to be using a big spherical probe head, on the orders of many centimeters in diameter at the end of a very long, boom in order to get decent measurements. The reason why I mentioned a very long boom is that the sheet thickness, so the natural barrier that exists between plasmas and surfaces, it's the lower the plasma density, the larger that sheet thickness is. And when you get to the sort of densities that you see in space, the sheet thickness can be like, 50 centimeters, a meter or whatever. So you want to make it so that the probe measurement is very far away from the body that's taking, from any other nearby surface to actually get data. So low. So let's say also, if your plasma chamber is driven by a remote plasma, so let's say you have a plasma that's separate and it's fed into the chamber and there's very low ion density. So let's say it's more of a reactive etch or something like that. To get any decent measurement, you want to have a spherical tip. Planar tip is normally used more often when you want to measure something directional. So like if you're looking at an ion beam tool, you might want to face the tip towards the beam because you're not interested in anything that sputters off the bottom where the beam is colliding or off the walls or whatever. So planar is usually more used for directional situations. But sort of most people that we deal with, they stick to the thin cylindrical probe, usually most applicable for typical industrial plasmas.
Okay, thanks, Tom. I think just at the top of the hour, we better call it for today. But just to say thank you again to everybody who's joined us, and to assure you that in the next 24 hours, you will get this recording of this presentation and a copy of the slides. But in the meantime, as Tom said, if you wish to reach out directly, info@impedans.com, and certainly we'll get back to you then. But thanks again for coming along today. Take care.
Thanks, everybody.